So hi again today. We're going to be working on 7.2 today, so you're going to want to start with this warm-up. I honestly can't think of any reason to help you with these problems. They seem pretty easy to me. We're going to use some of the knowledge we have about triangles, the fact that all the angles add up to 180, and also in number 3, parallelograms, and what's true about the opposite angles, and since it's a parallelogram, what's true about the alternate interior angles. So I'm going to just kind of leave you to handle this one, but I'll do a little preview on number 5 and 6. Since you're dealing with rotational symmetry, everything has rotational symmetry of 360 degrees. So for polygons, regular polygons, you divide by the number of sides. And I don't want to do that because there's only 2 of them, but it's going to be 360 divided by the number of sides. And that gives you the first number, and I guess I'll do this one, 360 divided by 5 gives me 72. So 72 is the main angle. But another angle that works is 144, which is 72 plus 72. Another angle that works is 6, carry nothing. 4 plus 3 is 11, 2, 16. I'm just adding 72 to that. Then we get 288, and then we're back to 360. Notice that there are 5 angles that work, and we added the number we got the first time till we get there. When you get to 360, you're done. Officially, the only thing we really need to do is say 72 is the rotational symmetry, but I like to talk about all of the angles that are less than 360 because it's interesting to know, hey, I could just turn it, but basically you turn it 72 degrees every time to get to the next angle, and so that's how that works. So go ahead, pause the video right now, finish the rest of these problems, and we will do answers in just a minute. So here we are. Number 1 was 22. Number 2 is 28. You can kind of see I wrote down what I did to find that one, where I found the other 2 angles and did the triangle. Number 3 is 30. Number 3y is 30 and x is 110 because opposite angles are congruent. Straight across the diagonal, they're the same. This is 55. That's 55. This is 35. So that's really it. Then we've got the 72 I did before. This became 45. So 45, 90, 135, 180, 225, 270, 315, and 360. So that's it for the warm-up. I hope that went so easy for you. I didn't expect it to be a big problem. Let's move on. We're going to be talking about 7.2 today, and we're moving into similarity. We've talked some about it, but Unit 7 is about circles, and we're going to specifically talk about circles here. The statement, all circles are similar, may seem intuitively obvious, which means you kind of know right away that's kind of dumb. And I've used this as an example many times when I talk about the difference between similar and congruent. I always pull out coins to do that because all circles are similar. And it is really clear. But we're going to go ahead and work on a proof of it to help us do this. Now, our proof is going to be about a sequence of dilations or rigid motion transformations to move one onto the other so that we can show that they're the same. So here we have these 2 circles. These are the 2 we're going to try to prove are congruent. We do not know what the radiuses are. All we know is that circle A is smaller than circle B. So here we go. It says to translate circle A until its center coincides with circle B, then enlarge circle A by dilation until all the points in circle A coincide with the points in circle B. Or you could shrink circle B by dilation until the points are on circle B that corresponds with A. Seems pretty easy and obvious. And by the way, that's the proof. But we didn't do anything except for that. We did, because that's what would happen. Take a look just really fast. I'm going to go ahead and grab a circle. Let's draw a circle real fast, make that a blue circle, and put it up here. And I want the circle not to have any filling inside, so let me make a new circle. No fill. Make it blue. Let's grab it. Circle, come on. And let's shrink that circle up. And so if I can, now my biggest problem here is I do not have a center, and the dilation on this is a little funky, but they're the same size. There it is. It's on circle, and it works. Notice it lines up perfectly. The circle was bigger, and now it's smaller, and they're the same. Let me put it over here. Let's see if I can make it the same size as this one. It's not lining up anymore. Let's try it again. Look, they're the same, and so it's true. And we're done. That's the proof. It's a pretty simple, straightforward thing, but we're going to play with it some more. After the translation, what is the scale factor? How much do we have to enlarge it? So what do you think? How much bigger do you think B is than A? So I want you to think about that for a minute. Go ahead and pause the video and think about what you think it is. And then vice versa, what's the scale factor? So you're aware there's no right answer because we don't have numbers. So if you said it's twice as big, or if you said it's 3 times as big, if you wrote that down, that's cool, but there's no such thing. I need to turn R1 into R2. That's what I know. So to make R1 equal, so R2, what am I going to do? Well, those are not numbers. So what do I do? Well, I know I'm multiplying to turn A into B. What am I multiplying by? Well, to turn R1 into that, I'm going to multiply by this. And then the R1 will cancel out and I'll be left with R2. So this is my scale factor. What about the other way? Well, that's R1 divided by R2. And yes, it would be nicer if we had numbers, but that's it. So this was 4 and this was 12. It would be 12 divided by 4, or a scale factor of 3. This would be 4 divided by 12, or a scale factor of 1/3. So we can do that with numbers, but without numbers, this is all we're doing. It's those two kind of crazy things because we don't have numbers. So they feel awkward and wrong, but they are right. And so we're done. We're going to move on to the next problem. So another way we might convince ourselves that two circles are similar would be to find the center of dilation that maps the pre-image points from circle A onto the corresponding points in circle B. So that might be helpful, is to actually dilate it. So what we're going to do is, how do we locate a center of dilation? So you had, I think, some homework about this yesterday to do a center of dilation. What we're going to do is we're going to use a ruler, and I'm going to line it up so it goes through A and B. Now, unfortunately, my rulers are locked up in the closet, so I don't have any, and that's all right. We don't need them. But notice what I'm doing is I'm going straight through the centers of the circles to kind of make sure that I'm gonna get there. Bye. Yep. Mom, she's saying goodbye. Go get her. I'm sorry, my aunt's leaving and I forgot to pause the video. But anyway, so you'll notice that I've drawn these lines through the centers, and then I did this other one tangent on the other side, and that is my center of dilation. So that helps, because if you recall, we were able to do this before with other points. So this is all that we're doing here. Draw some chords, triangles, or other polygons in the circle that would be similar. We're going to come back to that. We'll go ahead and pause this and make it start. We'll call this the end of this video. We'll get back to this in the next one.